Implementing principal component regression, PCR, efficiently requires the right tools, and modern statistical software provides multiple options for performing PCR seamlessly. Whether using Python, R, or MATLAB, each platform offers specialized libraries and functions that streamline the process of standardizing data, computing principal components, and fitting regression models. The choice of software often depends on the user's familiarity, the specific requirements of the analysis, and the available computational resources. Python is one of the most widely used languages for data science, and it provides powerful tools for performing PCR. The scikit-learn library offers functions for both principal component analysis, PCA, and multiple linear regression, MLR, making it easy to combine them for PCR. The typical workflow in Python starts with loading the dataset using pandas, standardizing the variables with standard scalar from sclearn.preprocessing, and then applying PCA using sclearn.decomposition.pca. Once the principal components are selected, a regression model is built using sclearn.linear model. Linear regression. Python's flexibility allows for additional customization, such as cross-validation using grid search CV, to optimize the number of principal components. The advantage of using Python is its scalability, allowing users to process large data sets efficiently and integrate PCR into broader machine learning workflows. R is another excellent tool for performing PCR, particularly favored by statisticians and researchers in academia. The PLS package in R provides built-in functions for both PCR and partial least squares regression, PLSR. The function PCR allows users to apply PCA and regression in a single step, specifying the number of components to retain using cross-validation. Data preprocessing, such as standardization, can be done using scale, wiki, and model evaluation metrics like R-squared and root, mean square error, RMSE, can be computed using functions from Caret. R's strong visualization capabilities make it easy to generate scree plots, residual diagnostics, and coefficient plots to analyze PCR results effectively. Many users prefer R for PCR due to its statistical rigor and extensive community support for regression analysis. MATLAB provides a user-friendly environment for PCR, particularly for engineers and researchers working in applied sciences. The built-in PCA function allows users to compute principal components, while regression modeling can be performed using FITL. MATLAB is particularly useful for handling large-scale numerical computations, making it a strong choice for high-dimensional data sets, such as genomics and environmental modeling. Users can also leverage built-in cross-validation tools to optimize the number of retained components. One advantage of MATLAB is its ability to integrate PCR with signal processing control systems and other engineering applications, making it a preferred choice in specialized fields. Each software has its strengths, and the choice depends on the specific needs of the analysis. Python is ideal for machine learning applications and scalable workflows. R is best suited for statistical modeling and visualization, and MATLAB is preferred for technical and engineering applications. Regardless of the tool used, the core steps remain the same. Standardize the data, compute principal components, select the optimal number of components, and perform regression. With the right implementation, PCR can be seamlessly integrated into data analysis pipelines, improving model stability and predictive accuracy. Now that we understand the tools available for implementing PCR, the next step is to explore how to apply PCR in practice using step-by-step guides. Whether using R, Python, or MATLAB, understanding the exact coding workflow is essential for effectively utilizing PCR in real-world applications. Let's take a closer look at how to implement PCR from start to finish in different programming environments. Applying principal component regression, PCR, in practice requires a step-by-step approach, ensuring that each phase from data preprocessing to model evaluation is executed correctly. In R, the PLS package provides an efficient way to perform PCR, integrating both principal component analysis, PCA, and multiple linear regression, MLR, into a streamlined workflow. Understanding how to implement PCR in R is crucial for statisticians, data analysts, and researchers who rely on statistical modeling for high-dimensional datasets. The first step in performing PCR in R is data preparation. The dataset must be loaded using reed.csvc or similar functions, ensuring that all variables are correctly formatted. If missing values are present, they should be handled using imputation techniques like nade.omit to prevent errors in analysis. Since PCA is sensitive to scale differences, the predictor variables should be standardized using scale so that all features contribute equally to the principal component transformation. With the dataset prepared, the next step is principal component analysis, PCA. The PRComp function in R is used to compute principal components and setting center true scale. True ensures that variables are standardized before transformation. The summary function is then used to examine the proportion of variance explained by each component, and a scree plot can be generated using scree-plot to visualize the optimal number of components to retain. Once the principal components are identified, the next phase is selecting components for regression. The PLS package allows users to specify the number of components in the regression model using the PCR function. By applying cross-validation with validation parse CV, the model determines the optimal number of principal components that minimize prediction error while avoiding overfitting. The selected principal components are then used as independent variables in the regression model, providing stable coefficient estimates free from multicollinearity. After fitting the PCR model, the final step is model evaluation. Standard performance metrics such as R-squared and root, mean square error RMSE, are calculated to assess how well the model explains the variability in the dependent variable. The summary function provides details on the model fit, while plot functions can be used to visualize residuals and model diagnostics. If needed, additional cross-validation can be performed to ensure robustness. By following this structured workflow, PCR can be efficiently implemented in R for high-dimensional datasets where traditional regression models struggle. However, R is just one option. Other programming environments, such as Python and MATLAB, offer alternative workflows for performing PCR. Understanding how to implement PCR across multiple platforms provides flexibility for data analysts working in different industries. To fully explore PCR's practical applications, the next step is to see how it can be implemented in Python. With powerful libraries like scikit-learn, Python provides a highly customizable approach to PCR, integrating seamlessly with modern machine learning workflows. Let's take a step-by-step look at how to apply PCR in Python. Applying principal component regression, PCR in Python, follows a structured workflow utilizing powerful libraries such as scikit-learn and pandas for data preprocessing, dimensionality reduction, and regression modeling. Python's flexibility makes it a popular choice for implementing PCR, especially in machine learning applications where scalability and integration with other analytical tools are essential. The first step in implementing PCR in Python is importing the necessary libraries. The key libraries used are pandas for handling datasets, NumPy for numerical computations, standard scalar from sclearn.preprocessing for data standardization, PCA from sclearn.decomposition for dimensionality reduction, and linear regression from sclearn.linearmodel for regression modeling. If cross-validation is required, cross-val score from sclearn model selection can be used to optimize the number of principal components. With the libraries imported, the next step is loading and preprocessing the dataset. The dataset is read using pd.read.csv, and missing values are handled appropriately to ensure a clean dataset. Since PCA is sensitive to different scales among variables, the predictor variables are standardized using standard scalar, which ensures that all features contribute equally to the principal components. The scaled data is then stored as a new variable ready for PCA transformation. The next phase involves computing principal components. Using PCA, NN components and none, all principal components are initially computed so that their explained variance can be analyzed. The explained variance ratio attribute is examined to determine how much variance each component captures, and a scree plot can be generated using matplotlib.pyplot to identify the optimal number of components. Based on this analysis, a reduced number of principal components is selected, typically those that explain 70–90% of the variance. Once the principal components are selected, the next step is performing regression. Instead of using the original predictor variables, the transformed principal components are used as input for a linear regression model. The fit method is applied to train the regression model on the principal components, and predictions can be made using predict. Since principal components are uncorrelated, this regression model avoids multicollinearity issues, resulting in more stable coefficient estimates. Finally, the model performance is evaluated using metrics such as R-squared, R2, and root mean square error, RMSE. These metrics help determine how well the PCR model explains variance in the dependent variable. Cross-validation using cross-val score can be applied to optimize the number of components, ensuring that the model generalizes well to new data. By following this step-by-step approach, PCR can be effectively implemented in Python, providing a scalable and flexible method for regression modeling in high-dimensional datasets. However, Python is not the only option. MATLAB also offers a structured environment for performing PCR, particularly in engineering and applied sciences. Understanding how PCR is implemented in MATLAB provides additional flexibility for researchers and analysts working with computationally intensive data sets. The next step is to explore the MATLAB implementation of PCR, where built-in functions simplify the process of principal component extraction and regression modeling. Let's walk through the step-by-step workflow of PCR in MATLAB. Applying Principal Component Regression, PCR, in MATLAB provides a structured approach to handling high-dimensional datasets, particularly in engineering, finance, and environmental sciences. MATLAB's built-in functions for principal component analysis, PCA, and multiple linear regression, MLR, allow for an efficient implementation of PCR, ensuring stability in regression coefficients while reducing multicollinearity. The first step in performing PCR in MATLAB is data preparation. The dataset is imported using functions like readTable or csred, ensuring that the predictor variables and the target variable are correctly formatted. If missing values are present, they must be handled before proceeding. Since PCA is highly sensitive to differences in scale, it is crucial to standardize the predictor variables using z-score, which ensures that all features contribute equally to the PCA transformation. Once the data is preprocessed, the next step is computing principal components. MATLAB's PCA function is used to transform the standardized predictor variables into a new set of orthogonal principal components. The function returns the principal component scores, eigenvalues, and the proportion of variance explained by each component. The explained variance is analyzed to determine how many components should be retained. A scree plot can be generated using plotcell to visualize the eigenvalues and identify the elbow point, where additional components contribute little new information. After selecting the optimal number of principal components, the next phase is performing regression. Instead of using the original predictor variables, the selected principal components are used as inputs for a regression model. MATLAB's fitlem function allows for the creation of a linear regression model using the principal components as independent variables. Since these components are uncorrelated, the resulting regression model is free from multicollinearity, providing stable coefficient estimates. Once the model is trained, the next step is evaluating model performance. Standard regression diagnostics such as R-squared, R2, root mean square error, RMSE, and residual analysis are used to assess how well the model explains variance in the dependent variable. MATLAB's predict function can be used to generate predictions, and cross-validation can be applied to ensure that the selected number of components optimizes the model's performance without overfitting. By following this step-by-step approach, PCR can be efficiently implemented in MATLAB for high-dimensional regression problems. MATLAB's strengths lie in its ability to handle large-scale computations and integrate PCR with other mathematical modeling techniques, making it a preferred choice for researchers in applied sciences and engineering fields.